In this lecture, we're going to look at different types of welfare measurements. Given an ordinal indirect utility function, psi function of prices, and remember I'm using an M for income, is equal to this direct utility function, which we've plugged into that direct utility function the various Marshallian demand functions. Total differentiating psi, we get that d psi is equal to the sum from I equals 1 to n of the first derivative of the indirect utility function with respect to pi times dpi plus the first derivative with respect to income times dm. Recall Roy's identity from the previous lecture that it's negative d psi partial of the indirect utility function with respect to price of any good I divided by the partial of the indirect utility function with respect to budget or income. And that gives us this result right here, which is tells us basically that the negative of the Marshallian demand function times the first derivative partial of psi with respect to m is equal to the partial of the indirect utility function with respect to pi. Also from the envelope theorem, we get this result here, and that enables us to rewrite the partial of psi with respect to pi, this right-hand side, as minus lambda qi p of m, so minus lambda times the ordinary demand function. Substituting that into number 2 here, into equation 2, gives us this following result here, where we have minus lambda times the sum of the derivatives of the sum of the Marshallian demands times dpi plus lambda dm. An adequate welfare measure then is given by the small change in dw, which we denote as welfare, which is equal to a small change in the indirect utility function divided by lambda, which implies that it's equal to the Marshallian demands times the small change in their prices, and then summed over that and the negative sign plus the change in income that occurs. This formulation is often used in deriving shadow prices for use in cost-benefit analysis. So this has an important, number 3 has an important function within cost-benefit analysis. The problem is that if we try to apply this particular equation to large or discrete changes, so instead of having a dw, we have a delta w. In order to do that, we need to integrate differential welfare changes between the initial and final situations so that we obtain the following, that the change in welfare is the integral, and I know that many of you haven't taken integration yet, but just go along with this, the integral, so the area underneath a welfare function from 0 to 1. So it's a discrete welfare change, and that's equal to the sum of all of the minus sum of all of these individual changes, these little changes, but then over an area of not a small price change, but a significant price change, plus the change in income that may or may not occur. Now, the right-hand side of 4, this here, is referred to as line integral. It's the sum of a series of integrals, each of which depends on the values of variables of integration in other integrals. So really what we're doing is we're summing all these little areas underneath a demand function, which is, this is the demand function, and we're going to sum these little areas between 2 points on the demand function, and we're going to break that area underneath the demand curve into very small slices, and we're going to sum those slices, And that's basically what we mean by the line integral. Now, the problem is that the final value of the change in welfare depends on the order of integration. In other words, it depends on which changes in prices we look at first. Do we look at good 1 changing, then good 2, then good 3, or do we look at good 3 and then good 1 and then good 2? So that order is going to affect the value of the welfare change. So the final value of the change in welfare depends on the order of integration, whether P1 changes from P01, from P10 to P11, before or after P2 changes from P20 to P21. So we can do that, we can show that in a diagram. So let's assume that M does not change, so the income doesn't change. And we look at a couple of changes here. First, we assume that, and note that we're using a 0 here to indicate the original position, the original price here, and a 1 to the situation where the price has changed. In this case, we've got a reduction in the price of 1 and an increase in the price of 2. So let's first take the reduction in the price of 1. So that means that this reduction in the price of 1 gives us this area A. And we're underneath this curve here with P1 and P2 set at 0. All right, P2, 0, the original position. So we gain area A. Then, after we've done that, we have a lower price of P1. So what happens is this demand for P2 shifts inwards, and then the price of P2 goes up. So then we lose area alpha. So we gain area A, we lose area alpha, and we measure the change in welfare by area A minus alpha. Now let's assume instead that P20 goes up first. So we get this increase from P20 to P21, and that means we're going to lose alpha plus beta. So we're going to get a reduction in our consumer surplus, if you like. Remember, this is P2 here with P1 unchanged at the original position. That's this demand function here, and we lose alpha beta because the price has gone up. So now we take the price decrease, and now we're no longer on this demand curve, but rather the relevant demand curve is this one, where the price of 2 is now the higher price. And in this case, when we reduce that price of 1, we now are looking at the area under this function rather than this function, which we saw in this case. So here we gain area A plus B. So the change in welfare, the total change is area A plus B, which we gain, minus area alpha minus beta. So that's the change. Now, there's no guarantee that B is equal to beta. So if this area here and this area here were the same, then we would have the same area here as in this measurement. So in other words, there wouldn't be any path dependency, as we call it. But there's no reason to think that beta and B are equal except by a fluke. So a mathematical theorem states that the values of the integral 4 of this integral up here, all right, is path dependent only if the matrix of derivatives of the QI functions is symmetric. In other words, that the partial of the QI, the ordinary demand function I with respect to Pj, is equal to the partial of the Marshallian demand J with respect to Pi, I not equal to J, and I and J running from 1 to n. For ordinary or uncompensated, we also call it uncompensated, and also Marshallian demand functions, there's no reason why 5 should hold. It is only true if there's no income effect. So in other words, there's no reason why B should equal beta. No reason why B should equal beta. So it turns out that the Marshallian consumer surplus, the area under Marshallian demand curve, is path dependent. It depends on the path we take to derive that welfare measure, and it's only if the income effect does not exist, then we have the same measure if we're absent an income effect. So let's review a minute. Let's recall what an income effect is. So if we're looking at a change in going from an original situation A, where we have this budget line, and we're going to now reduce the price of Q1. So we're going to shift that over. So now the appropriate budget constraint has this slope. So we go from A to E, which is our total effect. We can find the substitution effect by shifting this new price line, slope line, downwards until it's tangent to the original indifference curve. And we find that A to B is our substitution effect and B to E is our income effect. And it's only if we're looking at this shift that the welfare measure would be the same. So let's push that a little further, and we derive these Hicksian or compensated demand functions, which are associated with a particular utility level. So we have a Hicksian demand function, a compensated demand curve associated with U0, and another one associated with U1. And these pass through or intersect from above the Marshallian demand function, which is this one given by Q1 as a function of price and income, Q1 on this axis, P1 on that axis. And suppose that we reduce the price from the original situation, denoted P10, to P11, a new situation, one where the price of 1 is lower. Then we find that the consumer surplus is equal to alpha plus beta, so this area under the curve. But for a price reduction, all right, we get a second measure, which is known as compensating variation, which is given by this area alpha. And that's a true welfare measure because we're measuring it underneath this compensated demand function, which is a function of U0 of this particular indifference curve. So you can think of this as being U0, this indifference curve here. So let me maybe label that U0, and then this one is U1. So then we have this result here, but we also have another measure under this particular compensated demand function, which is based on the higher indifference curve. So now the price reduction is alpha plus beta plus gamma is the welfare measure associated with that price drop. So we have here that the equivalent variation is, that's what we refer to that as, is equal to alpha plus beta plus gamma. So now the compensated demand function really depends on what we take as our reference utility level or our reference indifference curve. If our reference curve is U0, then the compensating variation is the correct measure of well-being, alpha. So in other words, we're saying to people, well, you have a right to be on U0, but you don't really have a right to be on U1. If, however, you have a right to U1, to the higher indifference level, then we calculate the equivalent variation as alpha, beta, gamma. So in other words, if you have the right to the lower price, then the equivalent variation is alpha, beta, gamma. If you only have right to the higher price, then your compensating variation is alpha. And we will define those in a bit more detail later. But the thing to note here is that if we drop this price, all right, we can also, and get those welfare measures, we can also look at this as being an increase in price from P11 to P10. So if we increase the price, now we're saying, well, you've got a right to the lower price, but we're going to go to the higher price. So for a price increase, the consumer surplus, which we've denoted S, remains the same, but it's now a loss, minus alpha plus beta. Now the compensating variation is no longer alpha as it was with the drop in price. With the raise in price or the rise in price, it's alpha plus beta plus gamma. And the equivalent variation now is given by alpha. So at the point E, the ordinary and compensated demand curves intersect, which is important to note, in which case we write QI, PM. This is the Marshallian or ordinary demand function, and we plug in this expenditure function so that it's PE function of P and U. So in the end, we get this ordinary demand becomes a compensated demand where the price and level of utility determine what the demand will be. So the compensated demand is the same here as up here. So they intersect at these points, E and this point that's not labeled. So at point E is where they intersect. So we differentiate with respect to Pj, and we keep utility constant. So in other words, we're differentiating this one, and then we're differentiating the right-hand side of here with respect to Pj, and we take the derivative of Qi with respect to E, or M, our budget, and multiply it by the partial of E with respect to Pj, which then gives us dQi dPj plus partial of Qi with respect to M times Qj, because by Shepard's lemma, this is Qj. Rearrange this and we get the change in quantity as a result of a change in price for another good. So in other words, we're looking at the partial, so the change in Qi with respect to a price Pj, which is equal to the partial of Qi with respect to Pj when we hold utility constant, minus this Qj times the partial of Qi with respect to M. So the first part here is your total effect. The second component here is your substitution effect. And the third component is the income effect, which could be positive or negative depending on what is happening here. We can rewrite this as the change in Qi with respect to Pj equals to this S subscript ij, which is called the Slutsky matrix, minus Qj times the partial of Qi over M. And this expression here is referred to as the Slutsky equation. That's our Slutsky equation. And this Slutsky term right here is simply the partial of Q1 with respect to P1 and so on across, partial Q1 with respect to Pn, down here at the bottom row, partial of Qn with respect to P1, and then over in this corner, the partial of Qn with respect to Pn. Now we define the compensating variation, which we showed above, as the compensating variation of a move from situation 0, so a bundle of goods at situation 0, to a new bundle at situation 1, is the income that can be taken from a household in the new situation that leaves it as well off as in the old situation. So remember I said that you stay on that indifference curve U0 if that's what you have a right to, and you jump to U1, then we take income away from you so that you stay at U0, and that income that we have to take away is the compensating variation. If the household is better off in 1 than at 0, then the compensating variation is positive. If it's worse off, then it's negative, it's less than 0. The equivalent variation is defined in the following way. In going from situation or bundle of goods 0, the original, to 1, the equivalent variation is the income that must be given someone in the old situation so they are as well off as they would be in the new situation. If they are better off in the original situation than in the new one, then the equivalent variation is positive. If they're worse off in the original situation than in the new one, it's negative, the equivalent variation. Now, relating to the figure below, we want to get a little handle on compensating variation and equivalent variation and how we can measure it. Because remember, we don't see, we don't measure, we don't estimate a compensated demand function. We cannot estimate Hicksian demand functions. We only estimate Marshallian or ordinary demand functions. So we have to figure out, can we estimate compensating variation or equivalent variation, which turn out to be better estimates of welfare change than consumer surplus, because consumer surplus depends on the path that you choose to measure it. So let's start by looking at compensating variation, and let's use this figure below. All right, so the compensating variation is given by this. Let me just explain this figure a minute. So we have our original budget line here, and QN refers basically to all other goods except Q1, and we, depending on what Q1 is, and that maybe these indifference curves should actually intersect this axis, but I haven't drawn it that way, but that's okay from the point of view of the explanation here. So this point here represents our income. So if we don't buy any Q1, we don't purchase any Q1, then we have M0 amount for Qn. And our budget line is dependent on the slope of between Qn and Q1. And let's say we're on this indifference curve U0, and we're at the original point here, and we now change income. We have a change in income from M0 to M1, so we reduce our income slightly, and we reduce the price of P1, of Q1. And that means we get this new price line here, and the consumer is able to go from the original to the new position here. Now, if we look at it somewhat differently and look at the old price ratio, so this is the old price ratio, this is the slope of the line, and we now take a line parallel to it and shift it until it touches the new indifference curve U1, and we end up at this point here. So the actual shift is from 0 to 1, but if we retain the old price ratios, we end up here. If we look at the new price ratios, and we are originally now at 1, and we want to go down back to the new price ratio, but at the old indifference curve, so that we go from 0 to this point here. That's our substitution effect. These two lines are parallel, as indicated by the two arrowheads on there, and we're interested in measuring the differences between this and this. So the compensating variation is M1 minus E0, and we write that as M1 minus E, the expenditure function, at prices P1 and the indifference curve U0. We also have a change in income, which is M0, M1 minus M0. Here it is a negative number. And the compensating variation is equal to M0 plus M1 minus M0 minus the expenditure function up here. So what we've done is we've added and subtracted M0 to this equation there, and we now get M0 minus the expenditure required at prices P1 to achieve U0. That's the interpretation. The expenditure required at prices P1 to attain indifference curve or utility level U0. This then is our delta M, which comes from this part here. So substituting for that M0, the expenditure, so if we look here, the expenditure at P0, the original line, the original price line, at U0, which is this indifference curve, that's what M0 is, minus E P1 U0 plus delta M. Consider the compensating variation measure and apply a Taylor series expansion about the original price that we're given. So we have CV equals E, the expenditure at price 0, given U0, minus the expenditures at price P1, given U0, plus the change in the income. Now, taking a Taylor series expansion, we get about P0, we get E P0, U0, plus these partials of the expenditure function with respect to PI, and then summed over and multiplied by the changes in price, plus 1/2, the double sum over I and J of the second partial of the expenditure function P0 U0 with respect to D, the partial with respect to PI and then PJ, multiplied by delta PI, delta PJ, and then we have a remainder here, which we'll assume shortly that'll just go to 0. From Shepard's lemma, we get this result that the partial of the expenditure function with respect to any price PI is simply the compensated demand function there, and we just put that in place. We just assume that the C no longer applies because at the point that we're talking about, they intersect. So we just write this D squared E with respect to PI, PJ, derivative of the expenditure function with respect to PI and PJ is equal to the partial of the expenditure, partial of the compensated demand. So I'll write that again, of the compensated demand function with respect to PJ, and that's simply our Sij vector, or matrix. So then we can rewrite that expenditure function at P1 U0 around a Taylor series expansion of this around P0 is this result here. And we then take this and subtract it from the left-hand side, which gives us that. So the expenditure function at P0, U0 minus the expenditure function at P1, U0 is equal to the negative of the sum of the areas underneath the various compensated demand curves, but they're identical here to the Marshallian demand curves times the change in the prices, and then doing the same thing for that second order one. Now, if we go to a third order, then we can no longer measure it. All right, so at third order, we no longer measure it, so we assume that anything beyond the second order Taylor series expansion goes to 0. This remaining term goes to 0. So then we can write compensating variation is equal to the minus of the effects on the Marshallian demand times delta P minus 1/2 of all of this plus delta M. And that's a second order Taylor series expansion. The conclusion then is that everything can be observed through that Slutsky equation. So the Slutsky equation allows us to make these observations. We can find these values and thereby get the delta W. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.